Friends, welcome back to my YouTube channel. In this class, I am going to discuss PKNAG's problems of chapter 7, which are based upon the concept of entropy. So, question number 7.1 is like this. On the basis of the first law, fill in the blank spaces in the following table of imaginary heat engine cycles. On the basis of the second law, classify each cycle as reversible, irreversible, or impossible. So, on the basis of first law, we can fill in the blanks given in this table, and on the basis of second law, you can conclude whether the given heat engine cycle is reversible or irreversible, or it is not at all possible or impossible. Before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. You see, the first one is cycle A is that source temperature is 327 degrees Celsius and sink temperature is 27 degrees Celsius. Heat supplied to this heat engine is 420 kilojoule per second and heat rejected to the sink is 230 kilojoule per second. First we have to find out rate of work output in terms of kilowatt and then efficiency, and classify that. Eventually we have to classify whether this heat engine is reversible or irreversible or impossible. So first thing, we have to fill in the blanks. So we have to find out the rate of work output. For any heat engine cycle, according to the principle of energy conservation or first law of thermodynamics, net work output of any heat engine cycle is nothing but heat supplied to heat engine from source, of course, minus QR, that is heat rejected to sink. That means here QS is given, QR is given. We are to find out rate of work output, that is W net. So that is, this is in fact in rate form. So this is equal to, for the first case it is equal to 420 kilojoule per second minus 230 kilojoule per second, that is 190 kilojoule per second, or you can say 190 kilowatt. So here we have to write 190 kilowatt, fill in the blank, and the answer will be 190. Next is we have to find out the efficiency. So efficiency of this given heat engine cycle is nothing but net work output divided by rate of heat supplied, that is equal to 190 kilowatt divided by 420 kilowatt, that is equal to 45.23 percentage. In terms of percentage, the efficiency will be 45.23%. So whether this engine is reversible or irreversible or impossible, that we have to find out on the basis of second law of thermodynamics. You see, the maximum possible efficiency between these two given temperature is, maximum efficiency is that of a reversible heat engine according to Carnot theorem. Between any given two temperature levels, the maximum efficiency is that of a reversible engine operating between those two temperature levels, and that is 1 minus sink temperature expressed in terms of Kelvin, that is 27 degrees Celsius is the sink temperature. If you convert that into Kelvin, that will be 273 plus 27, that is 300, divided by 273 plus 327 is 600 Kelvin. So this is equal to 50%. So 50% is the efficiency of a reversible heat engine operating between these two temperature levels, that is 327 degrees Celsius and 27 degrees Celsius. But the efficiency of this particular engine is 45.23%, which is less than 50%. So it is an irreversible heat engine. So this particular heat engine is a case of irreversible heat engine, because between any two given temperature levels, only the reversible heat engine is having the highest of the efficiencies, and any other engine will be having less efficiency than that of a reversible heat engine according to Carnot theorem and its corollary. So this particular heat engine is a irreversible heat engine, and this result we can find out from Carnot theorem, that is second law of thermodynamics. So next bit is B. Here the source temperature is given, that is 1000 degrees Celsius, and sink temperature is 100 degrees Celsius, and heat rejected is given and efficiency is given. So we have to find out these two terms. One is heat supply and the net work output. So first one is, this is 4.2 megajoule per minute, and this we have to find out in terms of kilojoule per minute. So efficiency is 65%. Efficiency can also be expressed like this: 1 minus heat rejected by heat supplied. 1 minus heat rejected by heat supplied. So that is equal to 1 minus heat rejected in case of B is 4.2 megajoule per minute. This is rejection of it. This column is for heat supply, second column is for heat rejection, and in this case heat rejection is 4.2 megajoule per minute. So 1 minus 4.2 divided by QS, and this is already given to be 0.65. 65% is the efficiency. So 0.65, from which QS can be found out from this equation. 1 minus 4.2 by QS is this much. So QS is equal to, QS or heat supplied is equal to 12 megajoule per minute, or in terms of kilojoule this will be 12,000 kilojoule per minute. 12,000 kilojoule per minute. So here we have to fill in with 12,000 kilojoule. Heat supplied is this much. So we have to find out the rate of work output. So rate of work output will be rate of heat supply minus rate of heat rejected. So this is equal to, heat supplied is 12,000 kilojoule per minute. This is 12,000 kilojoule per minute, and this is 4.2 megajoule per minute. We have to convert that into kilojoule. 1 megajoule is 1000 kilojoule. So 4.2 multiplied by 1000 is 4200 kilojoule per minute. But we have to fill in this blank in terms of kilowatt. So to find out that, you have to divide it by 60. This is 7800 kilojoule per minute, and this is equal to 7800 divided by 60, that is 130 kilojoule per second, that is 130 kilowatt. So work output is 130 kilowatt. But how to classify this as whether reversible or irreversible? How to classify this as either reversible or irreversible? For that, we have to find out the maximum possible efficiency. Maximum possible efficiency between these two given temperatures is 1 minus the sink temperature, that is 100 degrees Celsius. The sink temperature, that is 100 degrees Celsius, has to be converted into absolute temperature. 273 plus 100 divided by plus 273, that is equal to 1 minus 373 divided by, this is equal to 0.707 or 70.7%. But the efficiency that we have calculated is, but for the given engine efficiency that is given is 65%. We need not calculate this. This is given in the question, that is 65%, 0.65. 65%, that means the efficiency of the given engine is less than maximum efficiency possible between these two given temperature levels. That means the engine is an irreversible heat engine. Then bit C. So this is to be classified as irreversible heat engine. When the efficiency of any engine is less than the maximum possible efficiency between two given temperature levels, then it has got to be an irreversible heat engine. And the efficiency of any reversible engine is the maximum possible efficiency, and that is 1 minus sink temperature expressed in terms of Kelvin divided by source temperature expressed in Kelvin. And third one is source temperature is given 750 Kelvin, source temperature is given, and sink temperature is 300 Kelvin. So net work output is given, efficiency is given. These two are to be calculated. So you see, efficiency is nothing but rate of work output divided by rate of heat supplied, and that is equal to 26 kilowatt. This is 26 kilowatt. This is 26 kilowatt is the rate of work output, but heat supplied we have to calculate. And this is equal to 0.6. 60% is nothing but 0.6. On equating this, we found Q dot S is equal to this much, and this is equal to 43.33 kilowatt. 43.33 kilowatt. Kilowatt is same as kilojoule per second, so 43.3. This is the heat supplied. And once we have got the rate of work output, we can easily find out the heat rejected, because according to first law, or according to principle of conservation of energy, for any heat engine cycle, Q dot S minus Q dot R is equal to rate of work output. So Q dot S is this much, 43.33 kilowatt, and rate of work output is already given in the question, 26 kilowatt. So heat rejected can be calculated. So Q dot S is 43.33 kilowatt minus Q dot R is equal to 26 kilowatt. So Q dot R is equal to 17.33 kilowatt, and then everything is filled up. This is 17.33 kilowatt. This is 17.33 kilowatt. So now we have got to classify it as reversible or irreversible or impossible. So now you see, maximum possible efficiency is how much? the maximum possible efficiency is 1 minus sink temperature is 300 Kelvin divided by 750 Kelvin. This is equal to 0.6, 60%. And you see the efficiency of this given heat engine is given to be 60%, and this is same as the maximum possible efficiency between these two temperature levels. That means this engine is a reversible heat engine. This engine is a reversible heat engine. So next question is like this. The source temperature is 700 Kelvin, sink temperature is 300 Kelvin, and this time heat supplied to the heat engine is given in terms of kilocalorie per hour, and heat rejected has to be calculated, and the rate of work output is expressed in terms of kilowatt. So once we are able to calculate the heat rejected, then we can easily find out the efficiency. Of course, right now also you can find out the efficiency and fill in this blank. So you see, first one is efficiency of this given heat engine is, actual heat engine is rate of work output divided by heat supplied. So that is equal to, work output is given in terms of kilowatt and heat supplied is given in terms of kilocalorie per hour. 2500 kilocalorie per hour. 1 kilocalorie is 4.2 kilojoule. And this is given to be in terms of hour, means if you want to convert this into second, then you have to divide it by 1 hour is equal to 3600 second. So now your numerator is in terms of kilowatt and this is also in terms of kilowatt. So this is going to be 3600 divided by 2500 into 4.2. This is kilowatt, this is kilowatt, and this is equal to 0.3428, or in terms of percentage 34.28%. So efficiency is calculated, and that is 34.28%. Next is, this one has to be calculated, heat rejected. So heat rejected can be easily calculated. QR is nothing but QS minus W, rate of work output. So rate of work output, first of all, QR has to be filled up in terms of kilocalorie per hour. So to find out QR in terms of kilocalorie per hour, we have to calculate rate of work output in terms of kilocalorie per hour also. But rate of work output is given to be 1 kilowatt, which is same as 1 kilojoule per second. It is given in the question. This is equal to, first we have to convert this second into hour. 1 kilojoule divided by 1 second is nothing but 1 by 3600 hour. This is 3600 kilojoule per hour, and 1 kilocalorie is equal to 4.2 kilojoule. So 1 kilojoule is equal to 1 by 4.2 kilocalorie. So rate of work output is equal to 3600 divided by 4.2 kilocalorie per hour, because it is 3600 kilojoule per hour, and if you convert that kilojoule into kilocalorie, this will be like this, and this is equal to 857.14 kilocalorie per hour. Now we have to find out, this is 857 point, sorry, this is work output, but we have to calculate rate of heat rejection. Work output is given, so rate of heat rejection is Q dot S minus rate of work output, and Q dot S is 2500 kilocalorie per hour minus rate of work output is 857.14 kilocalorie per hour, and this is equal to 1642.86 kilocalorie per hour. This is the heat rejected. So this is 1642.86 kilocalorie per hour. And now we have to classify this whether it is reversible or irreversible heat engine. You see, efficiency of this maximum possible efficiency between these two given temperature is 1 minus 300 Kelvin divided by 700 Kelvin. This is equal to 0.5714 or 57.14%. But we have calculated the efficiency of this actual heat engine is nothing but 34.28%. And since efficiency of this actual heat engine is less than efficiency of maximum possible efficiency of any heat engine between two given temperatures, then this is a case of an irreversible heat engine. So this is an irreversible heat engine. So next is question number 2. You see, the question is like this. The latent heat of fusion of water at 0 degrees Celsius is 335 kilojoule per kg. How much does the entropy of 1 kg of ice changes as it melts into water in each of the following ways? First one is heat is supplied reversibly to a mixture of ice and water at 0 degrees Celsius, and second part is a mixture of ice and water at 0 degrees Celsius is stirred by paddle wheel. In both cases, 1 kg of ice changes. 1 kg of ice melts into water. Latent heat of fusion of any substance is the amount of heat required to convert 1 kg of solid into liquid or to convert 1 kg of liquid into solid. So that is given to be 335 kilojoule per kg for water at 0 degrees Celsius. If you want to convert ice into water, you have to supply 335 kilojoule per kg, or if you extract 335 kilojoule per kg from water, you will find out ice at 0 degrees Celsius. So यहाँ जो state change हो रहा है in both the cases remain same. 1 kg of ice, state 1, suppose 1 kg of ice is converted to 1 kg of water. State 1, this is state 2. So that means, entropy is a state function. No matter whatever path the system may follow during this process, the change in entropy will remain same because entropy is a point function or property. So in both the cases, answer would remain same. But you see, first case, there is a mixture of ice and water. This mixture of ice and water, and heat is supplied to it. And this temperature at which heat is transferred, this temperature is 273 Kelvin. And during this phase change, since no rise in temperature take place, because this is a latent heat, so no, this is not a sensible heat that we can sense any rise in temperature. In fact, during this phase transition process, only heat is absorbed or heat is liberated, but no change in temperature is there. So when you supply this much of heat, suppose 335 kilojoule of heat, if you supply 335 kilojoule, then only ice is converted into water. So since 1 kg of ice is converted into water, means this much of heat is supplied to this mixture, ice plus water. And so if you consider this ice plus water as a system, this is a closed system, and you can apply both entropy balance principle, that is S in minus S out plus S gen is equal to delta S. यहाँ कुछ भी एंट्रोपी इन नहीं हो रहा है, एंट्रोपी इज ट्रांसफर्ड इनटू ए सिस्टम और आउट ऑफ ए सिस्टम विथ हीट or mass. There is no mass transfer into this system. Only thing, heat is entering into the system. So S in is of course there, but no S out, because neither mass is leaving, no heat is leaving, nor any heat is leaving also. So S in, and it is clearly given that heat is supplied reversibly. So in case of a reversible process, there is no entropy generation. No entropy generation. Entropy generation is a path function, and it is in existence only for reversible process. It is positive only for irreversible process, and for reversible process it is 0. So this is 0 and this is 0. So S in is equal to delta S. So S in is, that means entropy transfer into system along with this heat, and this is nothing but, you see here, heat is added to the system or supplied to the system, so plus Q divided by T, and entropy transfer with heat is calculated like this: Q divided by temperature at temperature of the boundary at which heat transfer takes place. When heat is transferred to a system, its entropy increases, and when heat is rejected out of a system, its entropy decreases. So this entropy change in this case will be 335, because this amount of heat is required at 0 degrees Celsius to convert 1 kg of ice into water, divided by 273, and mass is of course 1 kg, and entropy is an extensive property. So on cancelling this, the answer will be 335 kilojoule divided by 273 Kelvin. This is equal to, because 1 kg of ice is melted into water, 1.227 kilojoule per Kelvin. So this is given. How much does the entropy of 1 kg of ice changes? So mass is here 1 kg. But what about the second case? What about the second case? Here there is no heat is supplied, but some paddle wheel work is given into this system, or stirring is done. So W is given. Is, there is no entropy transfer with any kind of work. Entropy is associated only with a disorganized form of energy, that is heat. When heat is added to a system, entropy is transferred into it, and when it is rejected, then entropy of the system goes down. But with any kind of work, no entropy is transferred, neither into or nor out of this system. So since here pedal wheel work is given to this system, no entropy transfer takes place here. No entropy transfer takes place here, neither into nor out. And since this is an adiabatic system, then any kind of heat, no kind of heat actually gets out of this system also. So here if you apply this principle, entropy balance principle, this will be, so here S in is 0, S out is 0, but S generation will be there because it is not a reversible process. Some entropy will be generated within the system during this process, which will contribute to the increase in the entropy. But the numerical value of change in entropy will remain same, because in both the cases 1 kg of ice is converted into 1 kg of water. In both the cases 1 kg of ice is converted into 1 kg of water. So this is state 1, this is state 2. So delta S will be same in both these cases. But here in second case, no entropy transfer takes place, but some entropy is generated because the process is an irreversible one, and that entropy generation is equal to 1.227 kilojoule per Kelvin. So delta S will remain same because the change in entropy is a point function. Whenever a system moves from state 1 to state 2, no matter whatever path the system may follow, suppose this is a process takes place. If you follow through this path A, whatever change in entropy will take place. If you follow the path B, then also the change in entropy will remain same. So in both the cases, change in entropy will remain same, that is 1.227 kilojoule per Kelvin. So next question is question number 3 is like this. 2 kg of water at 80 degrees Celsius are mixed adiabatically with 3 kg of water at 30 degrees Celsius in a constant pressure process of 1 atmosphere. Find the increase in the entropy of the total mass of water due to the mixing process. Cp of water is 4.187 kilojoule per kg Kelvin. You see, suppose here there are two subsystems in this composite system. First one is 2 kg of water, 2 kg of water at a temperature of 80 degrees Celsius, and this is 3 kg of water at 30 degrees Celsius, and the mixing takes place adiabatically. So no heat transfer takes place between this composite system and the surroundings. And find the increase in entropy of total mass of water. To find out, we have to find out the equilibrium temperature. Obviously this temperature will go down and this temperature will go upward, because heat will be lost by this fluid and heat will be gained by this subsystem. If you consider this as subsystem 1, this is subsystem 2, then if you want to find out the entropy, increase in entropy of the total mass, then you can, because entropy is an extensive property, additive property, so we have to calculate the change in entropy of this subsystem 1, then change in entropy of this subsystem 2, and if we add them, then we will find the entropy change of the total mass of water. So first our objective is to find out equilibrium temperature, and first we can apply also the energy balance principle, which is nothing but E in minus E out minus E in minus E out is equal to delta E. This is the energy balance principle, and in this case no energy is entering into this system. If you take the complete system for energy balance analysis, then E in is 0 and E out is also 0. There is no form of energy leaving this total system. So that means, and this delta E is nothing but delta U, because delta, E is summation of Ek, Ep and U. Here no kinetic energy is there, no potential energy is there. So delta E is same as delta U. So that means from this we concluded that delta U is equal to 0. Delta U is equal to 0. And from this, you know, U is equal to MC into T. So delta U means, first we will calculate, that means from this delta U1 first subsystem and plus delta U of second subsystem is equal to 0. Since we are doing the analysis by taking this whole composite system as our system for analysis purpose. So this is delta U1 plus delta U2 is equal to 0. For first subsystem, that is 2 kg of water, delta U will be 2 into 4.187. This is C for water, specific heat, and change in internal energy will be TF minus 80, where TF is the final equilibrium temperature. इसका temperature decrease होगा, इसका temperature increase होगा. Just we want to what is the final temperature. Plus if you want to calculate the change in change in internal energy of the second subsystem, that will be this is final temperature and this is initial temperature. On equating this is equal to TF minus 30. This is equal to 3 into 4.187 into 30 minus TF. And from this, what we found is TF is equal to 50 degree Celsius. This is the final equilibrium temperature. Subsystem 1 will attain this temperature and subsystem 2 will also attain this final equilibrium temperature, which is 50 degree Celsius. So now we will calculate change in entropy of first subsystem. Delta S1 is nothing but dq by t, and dq is nothing but mc dt, m1 c1 dt by t. This is capital T1, this is capital TF, is equal to m1 c1 dt upon t. Integration limit is from t1 to tf. This is equal to m1 c1 ln tf divided by t1. This is equal to सबसिस्टम 1 का मास ये 2 kg है, 2 kg. So 2 multiplied by 4.187 ln. फाइनल टेम्परेचर इज 50 डिग्री सेल्सियस, मतलब उसको एब्सोल्यूट टेम्परेचर में कन्वर्ट करेंगे. 50 प्लस 273 323 डिवाइडेड बाई T1 इज 80 डिग्री सेल्सियस, 353 is equal to minus 0.74387 kilojoule per Kelvin. Similarly, if you want to calculate the entropy change of second subsystem, that will be is equal to m2c2 ln tf upon t2, and this is equal to 3 into 4.187 ln 323 divided by 303, 30 degrees Celsius. Second subsystem is at 30 degrees Celsius. So this is equal to 0.8028 kilojoule per Kelvin. So total system, if you calculate the change in entropy of total system, total composite system means total system, this is, so this will be delta entropy change of first system subsystem plus entropy change of second subsystem, because entropy is an additive property. This is minus 0.74387 plus 0.8028 kilojoule per Kelvin. This is equal to 0.0589 kilojoule per Kelvin. When the delta S surrounding is already 0, because this is an adiabatic process. No heat will be transferred between the surrounding and system. This is an adiabatic process. So this is the delta S system in this case, and this is delta S surrounding. So delta S universe will be, delta S universe is nothing but delta S system plus delta S surrounding. Delta S surrounding, this is delta S system, and delta S surrounding is 0. So that means delta S universe in this case is 0.0589 kilojoule per Kelvin, which is a positive value. And when the delta S universe is greater than 0, the process is an irreversible one. So we can conclude that this mixing process is an irreversible process. Mixing process is an irreversible process. So thanks for watching. That's all.